Statistics. Yeah, I know. The word itself can sound a little scary, right? You probably picture these massive spreadsheets and, I don't know, scary-looking formulas. But what if I told you that statistics is really just the art of storytelling? Seriously, let's dive in because by the end of this explainer, you're going to see exactly how to turn these intimidating terms into really powerful tools for understanding the stories hidden inside data. This quote right here, it gets to the very heart of the problem, doesn't it? A spreadsheet just full of numbers is, well, it's just noise. It's silent. It doesn't actually tell you anything on its own. To make it speak, to give it a voice, we need to apply the grammar of statistics. And that's what turns all these disconnected facts into a story that we can actually understand. So in the world of statistics, there are really two main branches. I want you to think of it like this. Descriptive statistics is like writing a book report. You've read the entire book, you know everything that happened, and your job is just to summarize it with 100% certainty. Inferential statistics, on the other hand, is like reading only the first chapter and then trying to predict the ending. For this explainer, we're going to focus on mastering that book report, learning how to perfectly describe the data we have right in front of us. All right, so here's our game plan. First, we're going to learn data's secret language. Then we'll figure out how to find our typical student. After that, we'll see if our data is all clustered together or if it's kind of scattered. And finally, we'll put the whole thing together to tell one complete story. Okay, first things first, and this is probably the most important step of all. Before you can do anything with data, you have to know what kind of data you're dealing with. I mean it. If you get this step wrong, your entire story, well, it's just going to fall apart before you even begin.
So data pretty much comes in four main flavors, and you gotta know the difference. You've got nominal data, which is just names, categories, like ethnicity. Then there's ordinal, which has a logical order, like parental support, going from low to high. Then you get to the numbers. Discrete data is stuff you can count, like absences. You can have 5 absences, but you can't have 5.27 absences. And continuous data can be anything in between, like a GPA, which you could measure out to 1,000,000 decimal places if you really wanted to.
This brings up a really interesting question. A student ID number. It's a number, right? So can we average it? The answer, it's a hard no. And why is that? Because it's just a label. It's actually nominal data disguised as a number. Calculating the average student ID would be totally, completely meaningless. And that right there is why we have to classify our data first. All right, so we know what kind of data we have. Now the fun begins. The very first step in telling any data story is to find the main character, or in our case, the typical value. We do this using something called measures of central tendency. The two big players on this field are the mean and the median. The mean is just the average you're used to. It's like everyone in a room throws their money in a big pot and then splits it evenly. Every single dollar from every person matters. The median, though, is different. It's all about that middle person in line. If you line everyone up from shortest to tallest, the median is just the height of the person standing in the dead center. It doesn't care how tall the tallest person is at all, just who's in that middle spot.
To really get this, let's paint a picture. Imagine a room with 10 teachers, and they all make exactly $50,000 a year. The mean salary is $50,000, and the median salary is also $50,000. Makes sense. But then, a billionaire walks into the room. So what happens to the median salary? Nothing. It's still $50,000. One of the teachers is still the middle person. But the mean salary? It goes through the roof. It skyrockets to over $90 million. This is the mean's biggest weakness. It's incredibly sensitive to those extreme values, which we call outliers.
And hey, let's not forget about the mode. It's the simplest of the bunch. It's just the most popular choice, the thing that shows up most often. But it has a superpower. It's the only one of these measures we can use for that nominal, category-based data. You can't average ethnicities, right? But you can absolutely find the most common one. That's the mode. So we've found the center of our data story. But that's only half the picture, isn't it? We need to know if all the other data points are clustered tightly around that center, or if they're just scattered all over the place. To figure that out, we use measures of variability. The easiest one to understand is the range. It's just the highest value minus the lowest value. Simple. It gives you the full span of your data. But you can probably guess its weakness, right? Just like the mean, it's totally defined by the two most extreme points, which makes it really sensitive to outliers. So for something way more solid, we have what's called the interquartile range, or IQR.
And I know, it sounds complicated, but it's really not. Just picture this. You line up all your data points from lowest to highest. Then you ask the bottom quarter of them to just leave. Then you ask the top quarter to leave. The range of the people who are still left in the middle, that's your IQR. By ignoring the extremes, it gives us a much better idea of the spread of the core 50% of our data.
All right, now for the gold standard of spread, standard deviation. I know, the name sounds intimidating, but stick with me. It's actually a pretty simple idea. It's just one number that tells you the typical distance of any given data point from the average. So a small standard deviation means your data is really consistent and packed together. A large one means it's all over the map.
Okay, we've gathered all our tools, theory time is over, now for the payoff. We're going to use every single thing we just learned to analyze one variable, student GPA, and we are going to uncover the story it has to tell. First up, we calculate the mean GPA, and it's 3.05. Remember, this is the mathematical balance point. It's like we took every single GPA, put them in a pot, and gave everyone an equal share. Next up, the median, and that comes in at 3.15. This tells us something different. If we lined up every single student by their GPA, from lowest to highest, the student standing right in the middle of that line has a 3.15. Interesting. That's already a clue that something's going on here. And our last piece of the puzzle, the standard deviation, is 0.6. What does that tell us? Well, it means a typical student's GPA is floating somewhere around 0.6 points above or below that mean of 3.05. It gives us a sense of the spread. Okay, now let's put it all together. The mean is 3.05 and the median is 3.15. The mean is lower than the median. Now think back to our billionaire example. What does it mean when the mean gets pulled in one direction? It means an extreme value is yanking on it. The story is really starting to come into focus now. And here it is, the full story. Because that mean is lower than the median, we know the data is what we call negatively skewed. In simple terms, that means most of our students are clustered up at the high end of the GPA scale. They're doing really well. But there's a tail of lower performing students that's pulling that average down. And that's not just a number, that's an insight. It tells a story of a high-achieving student body, but it also shines a spotlight on a group that might be struggling and could use a little extra support. See, an actionable story, all from just a few numbers.
So, you see, once you learn the language, data stops being just a bunch of silent random facts. It becomes a collection of stories just waiting for someone to tell them. So the real question is, what story are you going to uncover next?